You are tuned to Iri-e-learning, and I am your host, Teacher. In this periodic table and periodicity lesson, we will take a brief look at the history of the periodic table. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to outline a brief history of the periodic table, particularly the work of Johann Deberheiner, John Newlands, and Dmitri Mendeleev. Also identify the features of the modern periodic table. Some of the initial work on classifying known elements started in the early 1800s. Chemists have always looked for ways of arranging the elements to reflect the similarities between their properties. Note that historically there were two main ways to categorize elements. One, according to their physical and chemical properties, and two, the relative atomic weight, which is equivalent to the mass number. Keep in mind that the atomic number was unknown to scientists during the early 1800s, since subatomic particles, protons, neutrons, and electrons, had not yet been discovered. Hence, the reason for arranging the atoms according to the atomic weight, which they knew. Many scientists made attempts to arrange the known elements during the 1800s. However, we will only review a few, starting with Johann Deberheiner. He was a German chemist who in 1829 recognized similarities in the properties of groups of three elements, such as lithium, sodium, and potassium, and then again chlorine, bromine, and iodine. These triplet of elements that had similar properties he called triads of elements. Deberheiner was able to predict the property of the central element from the other two properties in the triad. For example, bromine occurred between chlorine and iodine. He knew that chlorine was a gas and iodine was a solid, therefore bromine would be a liquid. And in fact, bromine is a reddish-brown colored liquid. By 1863, John Newlands, an English chemist, recognized that every eighth element appeared to have similar properties. As a result, Newlands listed a few known elements into rows of 7, as illustrated in the portion of Newlands' table shown below. This rule became known as Newlands' law of octaves. However, this pattern did not work because he assumed that all the elements had been found, even though new ones were still turning up regularly. He proceeded to fill out his octaves, although some elements were not similar at all. He also made blunders such as putting two elements into the same position in the arrangement to make everything fit. The pattern became distorted, particularly for metals such as iron, copper, and zinc. By 1869, a Russian chemist, Dmitri Mendeleev, arranged about 50 known elements in order of increasing atomic weight as Newlands did. However, Mendeleev left gaps or spaces in his arrangement based on predicted properties for elements not yet discovered. As a result, he kept elements with similar properties in the same vertical column. The asterisks in Mendeleev's table of elements shown here represent the gaps left for unknown elements of that time. Leaving the gaps was a very clever decision. When new elements with specific predicted properties were discovered, they fitted perfectly in the respective gaps or spaces. Mendeleev's table of elements, as partially illustrated here, became very popular for cataloging and understanding the elements. Consequently, it became the foundation on which the modern periodic table was developed. As we just learned, Mendeleev's table of elements became the foundation on which the modern periodic table developed. At the start of the 20th century, scientists began to discover more about the atom, including that the atom was made up of smaller subatomic particles, protons, neutrons, and electrons. As a result, the premise was set for arranging elements in the modern periodic table. Consequently, the modern periodic table arranges the elements in order of atomic or proton number instead of atomic weight. So now we describe the periodic table as the arrangement of known elements in the order of increasing atomic number. Here is a copy of what the modern periodic table looks like, particularly the one you would use for examination purposes. However, notice that this is not a complete periodic table because the lanthanides, elements with atomic numbers 58 to 71, and the actinides, elements with atomic number 90 to 103, have been omitted. Let us examine some of the features of the modern periodic table using only the first 4 rows. Feature 1. The elements are arranged in order of increasing atomic number. We can follow the red dots from left to right for each progressive row. The second feature, elements with similar properties form columns. Each vertical column, as shown by each running red arrow, contains elements with similar properties. For example, lithium, sodium, and potassium occur within the first column, so their properties are similar. The vertical columns are called groups. The groups are assigned numbers 1 to 7 and 0. Previously, the groups were numbered using Roman numerals. However, over time, we have moved away from that notation and simply use the Arabic numerals. Those are the digits we are accustomed to using as represented here. The group number is very important because it indicates how many electrons are on the last shell of the atom, with the exception of group 0. Therefore, all the atoms of the elements listed in group 1, that is the first column, will have 1 electron on the last shell. Likewise, the atoms of group 2 elements will have 2 electrons on their last shell, and so on up to group 7. Now, because the elements within a particular group have the same number of electrons on their last shell, they will also have similar properties. Group 0, on the other hand, indicates that the last shell of all the atoms listed in this column contains the maximum number of electrons. Therefore, we say that the last shell is full. That is, the last shell or valence shell contains the maximum number of electrons. The third feature of the modern periodic table, elements are arranged in horizontal rows called periods. And we can see here the periods going across for the first 4 rows of this periodic table. Now, the first row we can see consists of only 2 elements, hydrogen and helium. The second row starts with lithium and terminates with neon. The third row begins with sodium and terminates with argon. The fourth row begins with potassium and terminates with krypton. Also notice that the periods are numbered. The period number is also significant because it tells us a number of shells present on the atoms within a given row. So all the atoms in period 1, which is hydrogen and helium, will have only 1 shell each. All the atoms present in period 2 will have 2 shells each, and so on. There are 4 groups in the periodic table that are assigned special names. Group 1, alkali metals. Group 2, alkaline earth metals. Group 7, halogens. Group 0, inert gases, previously called noble gases. Types of elements in the periodic table. The elements in the periodic table are further subdivided into 3 categories: metals, semimetals, also called metalloids, and nonmetals. However, before we begin to look at the 3 categories just mentioned, let us direct our attention to the bold step-like demarcation drawn here on the periodic table. This step-like boundary separates the 2 main types of elements on the periodic table: the metals, which are to the left of the boundary, and the nonmetals to the right of the boundary. The metals which are to the right of the boundary are of 3 types. First, the section in blue referred to as reactive metals. These are the metals of groups 1 and 2. As the name suggests, these elements are highly reactive and will react vigorously with other elements such as oxygen or chlorine and with substances such as water. Due to their high reactivity, group 1 metals in particular must be stored under oil to prevent them from reacting with air and water vapor. These metals are also very soft and can be easily cut with a knife. The second group of metals occur in the yellow section and are called the transition metals. This section consists of most of the metals we would think of when we hear the word metal, such as iron, copper, zinc, silver, platinum, and gold. The transition Transition metals are not usually very reactive. In fact, some like silver and gold are unreactive, and the reason why they are found in nature as the element. The compounds of transition metals are usually brightly colored with blues and greens, purples, yellows, oranges, etc. The third category of metals highlighted in green are the post-transition metals. Post-transition simply refers to the position of these metals in the periodic table, in that they occur to the right or just after the transition metals, moving of course from left to right on the periodic table. Post-transition metals are often soft and brittle with melting points lower than those of transition metals. Bordering the boundary mark are 8 elements in gray. These are the semimetals, also known as metalloids. The 8 metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. The metalloids have properties that resemble both those of metals and nonmetals. For example, silicon is lustrous or shiny like a metal, but brittle like a nonmetal. All other elements in the periodic table are nonmetals. That is a section in orange as well as purple. However, we will give special mention to the elements in purple because of their unique properties. Nonmetals are elements with low melting and boiling point, and many are liquids and gases at room temperature and pressure. The elements highlighted in purple are the inert gases, previously called noble gases. As the name suggests, all the elements in this group are gases. The inert gases are generally unreactive, that is, they do not react with other elements because all their shells contain the maximum number of electrons. Let us quickly review what we just discussed about the type of elements in the periodic table. The elements in the periodic table are classified as either metals, semimetals, also known as metalloids, and nonmetals. The metals, of course, are of 3 types. We have the reactive metals, which are the groups 1 and 2 elements. We have transition metals and the post-transition metals. The metalloids border the boundary that separates the metals from the nonmetals on the periodic table and include boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. There are only a few elements that are nonmetals, inclusive of the inert gases. The inert gases were specially mentioned because they're all gases and generally unreactive. We have covered quite a bit in this lesson, so let us summarize the important points. First, the elements in the ancient periodic table were arranged according to atomic weight and properties. Scientists such as Johann Debeheiner, John Newlands, and Mendeleev made contributions to the development of the periodic table. Mendeleev left gaps in his table of elements for unknown elements, which fit perfectly upon discovery. Mendeleev's table of elements became the foundation for the modern periodic table. The elements of the modern periodic table are arranged in order of increasing atomic number, that is, the proton number. The elements are also arranged in columns called groups and rows called periods. The group number tells the number of electrons on the last shell of the atoms. The elements in the same group have similar properties because they have the same number of electrons on the last shell. The period number indicates the number of shells the atom has. There are some groups with special names: Group 1, alkali metals; Group 2, alkaline earth metals; Group 7, halogens; Group 0, inert gases, previously referred to as noble gases. The elements in the periodic table are further categorized as metals, metalloids, and nonmetals. It's quiz time, and you have 5 seconds to answer each question after it is read aloud. Question 1. Identify the scientist who left gaps in his arrangement for unknown elements that had specific properties. A. John Newlands. B. Dmitri Mendeleev. C. Johann Debeheiner. D. John Dalton. Of course, the answer is B, Dmitri Mendeleev. Question 2. What is the name given to atoms with 7 electrons on their last shell? A. Alkaline earth metals. B. Inert gases. C. Halogens. D. Alkali metals. The answer is C, halogens. Of course, if there are 7 electrons on the last shell, it means those atoms are in group 7, and group 7 has a special name, halogens, sometimes pronounced halogens. Question 3. Which statement gives an accurate description of the arrangement of elements in the modern periodic table? A. The elements are arranged in order of increasing atomic number. B. The elements are arranged in order of decreasing atomic number. C. The elements are arranged in order of increasing atomic mass. D. The elements are arranged in order of decreasing atomic mass. The answer is A. In the modern periodic table, the elements are arranged in order of increasing atomic number. Question 4. All the following statements are correct about the modern periodic table except A. Elements are arranged in order of increasing proton number. B. Elements with similar properties are in the same group. C. Elements that have the same number of shells are in the same row. D. Elements with similar chemical properties are in the same period. The answer is D. Elements with similar chemical properties are in the same period, and that statement is incorrect about the modern periodic table. Question 5. How were elements categorized during the 1800s? A. The elements were arranged according to their atomic weight and properties. B. The elements were arranged according to their atomic number and properties. C. The elements were arranged according to their atomic weight and atomic number. D. The elements were arranged according to their physical properties only. The answer is A. The elements were categorized according to their atomic weight and properties during the 1800s. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.